Uh, okay. So, since I'll be teaching your batch for the first time, let me just make a few things clear. Um, so, the way I teach this course usually, or I have been teaching this course usually, is through slides, but this time around, I may be doing a combination of slides and notes, class notes. That's why you are seeing this whiteboard. Um, so before I start, I would like to get some information from you all. So you have thus far done only one course in statistics, that is your statistics one course, and you have also done a probability course in your second year. So I would like to know what all things have you covered in your statistics one course?
We
Any
did
of you can
descriptive
answer.
statistics, and then
Mhm.
we did statistical inference and the basic part. So, like Kramer-Rao and uh,
Okay.
Kramer-Rao we did, and then we did testing of hypothesis. We did very basics. So
Okay, so you have done a bit of point estimation and then
yes,
Cramer lower bound
point estimation we have
and
done.
then a bit of testing of testing of
Yes,
hypothesis. Okay,
yes,
and have you done so in your probability one or in your statistics one? Have you done things like weak law of large
yes,
numbers,
yes. We did in
central
probability one.
in probability
Yeah.
one? Okay, but I test you have done the basic statement and all, right? You did
Yes,
not go into a lot
basics
of
only.
details.
Yeah.
Okay, okay, all right,
Modes of
fine.
convergence.
Yeah, yeah, fine, fine. Okay, okay, all right. So this course, because it's a general course, obviously it will have the general division of 20 marks being mid-sem and then 30 marks being internal assessment and 50 marks as your end-sem. Um, both your mid-sem and your end-sem will obviously be online exams. So I'll be giving question paper to all of you and be answering them. That's fine. And the internal assessment, I will perhaps, so of the 30 marks of internal assessment, I will give you some assignments to solve, of course, and so that will constitute one part of the internal assessment. The other part of the internal assessment will obviously be your class performance and how many classes you're attending and roughly that kind of stuff. And I might also take because there are only 6 or 7 of you I saw, so I might take or I might take Viva for all of you. So that might constitute 10 marks of the internal assessment. Okay, so that will roughly be how the course will run. Um, so uh, the course, I will not follow one single book, but maybe multiple books. But obviously, one very or a couple of books that you can perhaps study for this particular course would be one of them is called Introduction to Probability and um, Statistics, and the author is V.K. Rohatgi and A.K.M. Saleh. So that's one book. The second book, I don't remember the title of the book. I think it's called Introduction to Mathematical Statistics or something. I don't remember the title exactly. This book is by Casella and Barger. I believe it's called Introduction to Statistical Inference or Mathematical Statistics. I don't remember. But the authors are Casella and Barger. So these two books, I will mostly follow bits and pieces of these two books, and that's how my lecture notes are designed. But from time to time, if I refer to any other book, then I will obviously let you know. But in particular, I mean, if you're looking at a general introduction to a bit of probability theory, distributions and all, multivariate distributions and so on, as well as statistics, this is a very nice book. And obviously, Castellan-Berger, the nice thing about Castellan-Berger is that it has a lot of problems, lots of problems which you can attempt and try to do. It's a very nice book. Okay. So that's about the books of this course. So let me ask you also another thing. How much of I mean, multivariables or multivariate distributions or things like that have you done? Bivariate distributions, bivariate normal. Are you familiar with these kind of things? Yes.
We have done bivariate, but we haven't done much of multivariate.
You have done bivariate, not much of
Bivariate normal distribution, not
bivariate
bivariate
normal
general, like
distribution.
bivariate normal.
Okay. Yeah,
Yeah.
bivariate normal is good enough, but at least you know how things work in case of bivariate or in general multivariate, right? Or you're not that comfortable
So
with
not
multivariate.
multivariate, bivariate we know. Yeah.
Okay, okay, all right, fine. Okay, so I will perhaps run you through or give you some little notes so that you can study some of these things. Okay, okay. So so let's start with this course. So this course is obviously on statistical inference. So you have done some bit of statistical inference. So let me ask you, what exactly do you understand when somebody talks about statistical inference per se? You have done one course, so you should have some understanding. So can you tell me what exactly do you understand by this term statistical inference?
Sir, I think we have statistical data and we're trying to understand it, like what information it's giving us.
Okay, okay, that's a fair enough answer. So the course is essentially of this kind. Okay, so let's see. So what is this course about? So what part is obviously so we generally talk about statistical theory. Then the what part is obviously the rigorous study of the procedure of extracting information from data using mathematical slash statistical tools. That's obviously statistical theory or inference. Uh, and how do we do it? So we just think of data as observation or outcome of a probabilistic experiment. So that's kind of like what we do and how we do. And obviously, probability theory is generally in natural language to describe any kind of uncertainty about a particular system or to understand a particular system. And data is what we get to observe from that system, the information that we see from that system, and based on that information we will try to understand that system better. What is a suitable model for that system, or how that system can be explained based on this data. So all of these things fall under the purview of what is called statistical inference. Okay? And the job of any statistician is that given in an outcome or given a particular data from a particular probabilistic experiment, you need to tell something more than what is already known. Okay? So this data is kind of evidence, and based on this evidence you're about to make some sort of inference. So the word English word inference is essentially meaning that I want to infer something about this experiment. Okay, so what is it that what are the questions that we ask in statistical inference? So questions in statistical inference. So what is it that we ought to know? Okay. So one of these questions would be, are the data consistent with a certain model that is proposed to explain the experiment. That could be one question, or the other question could be, given a family of models proposed to explain the experiment, can we determine which model generated the data at hand? So you see, these two questions, although they apparently look similar, but are very different. In the first question, we are asking that, okay, we are proposing a particular model, and suppose, and I will come to later how we propose this model and so on. But suppose we are proposing a particular model to understand a particular system or understand a particular experiment. What we are trying to get, what we're trying to answer is whether the data at hand supports this hypothesis, or supports this model for the experiment. Okay? So the first question is essentially what falls under the purview of testing of hypothesis. Okay. The second question is a somewhat different question. So now, instead of proposing one model, suppose I have a class of models. Okay, there could be a class of models which is, say, indexed by some unknown parameter or something of that sort, but there is a class of models, and I do not know a priori which model is true. That I don't know, but there is some true model. That much I can assume, that amongst this class of model there is a true model which I don't know. But now, based on the data at hand, can we now determine that which is the true model? Okay. So this essentially comes under the purview of point estimation, or a more general question of interval estimation. Okay. So this is essentially, in general, estimation. And there could be other different questions also, but mostly we will try to frame the questions either in type 1 or in type 2. So either as question 1 or question. Okay. And the way we propose models, that will essentially come from your field knowledge. Suppose you are trying to explain some physical phenomena, and obviously based on some knowledge from physics, you will try to propose a model. Okay, so this will be a hypothesis that we have, a hypothetical model, and then we will run several experiments of this physical phenomenon, and we will get data. Now we have our hypothetical model, we will get data, and then we will try to understand that whether the hypothetical model that we had in mind, whether that is true or not, or if we have proposed a whole class of hypothetical models, we will try to understand which is the truth. So that's essentially what this thing is about. So let's give you a little example, a very basic example of an experiment that you have done so far. Suppose have a coin, and you flip it 10 times. So this is a very simple probabilistic experiment that you have obviously seen in your probability 1 course. So obviously, if I call my outcomes of the experiment x1, x2, x10, these are outcomes. Of the experiment, obviously these outcomes would be either head or tail, or 0 or 1, whichever you want to tell. So the possible questions that one can ask will be: is the coin fair? That is to say, whether the probability of falling head is half. Okay. The other thing could be what is the probability of success given the data at hand. Okay. Now, obviously, you can see that if suppose in your 10 flips of the coin, suppose you get cannot be anything arbitrary between 1. Definitely, it cannot be 0, nor can it be 1. Okay. So obviously, your data will determine what can be the different probabilities of success, okay, or what can be plausible values of the probability of success. The third question can be how much error do we make when trying to decide the above from the observed data. Okay. So obviously both 1 and 2 will crucially depend on the data. So and data is only just 10 observations. Okay. So obviously you are bound to make some sort of an error, and this is what is typically called uncertainty quantification, or a quantification of the error that the procedure already incurs. Okay. That could be a fourth question. How does the answer change if the data changes. Okay. That would be another question. The fifth question: is there a quote-unquote best solution of the above problems? So this is a very important question, and we'll come to several such notions of best in this entire course, and you will see that there is no single notion of best. Whatever notion of best that we will do will depend on whatever criterion you are using. Okay? So that could be another question. And one last question could be, how do the answers change if the number of tosses keep on increasing? So in this example, I told you 10 tosses, but suppose I was in a situation to generate more data. Then what can be said about the behavior of these solutions that you have proposed? What can be said about the behavior of such solutions? In general, if instead of 20 tosses, you might look at n tosses and then let n to grow to infinity. Okay. Suppose in a hypothetical situation, you might have an infinite number of tosses. Then what happens? Then is it so that we approach the truth, or because in general, if you think about an infinite number of tosses, then you're essentially getting all of the different possibilities from that experiment. So if I have all of the different possibilities of that experiment, then intuitively or very naively thinking, I should be able to best describe the experiment, or I should be able to know the experiment fully. So do things of this kind happen? So all of these questions, which I have written down from 1 to 6, all of these questions fall under the purview of statistical inference. Okay, and we'll answer most of these questions throughout this entire course, okay, in several ways. Okay, so that's good. So in order to do several of the things that we do, I will or we will need some prerequisite things. Okay. You have already said that you have done a bit of by very normal distributions. I will give you later on, or I will upload on VLearn a little short notes for you all to read, which will be a brief review or a recap of most of the probability distributions that we have seen, a brief recap of or a brief overview on on several variables or multivariate random variables, what it means to say distribution function, and how do we generate conditional distributions, marginal distributions, and so on and so forth. I will also give you some additional things. So that will be part of the notes, because there is really no point in discussing those things in a class. Okay, but that you'll be able to read. But I will now like to digress a little bit and give you some overview on certain other things also. So this overview essentially is related to this question number 6 that I have mentioned. What happens if the tosses keep on increasing? Okay. And there's a reason why we want to answer, we want to look at this hypothetical scenario of the number of experiments, or the number of data that you have at hand, that number potentially growing to infinity. Okay. And the reason is the following. Many a times what happens is that when you propose a statistical technique, and if you want to evaluate the performance of the statistical technique. So look, we are statisticians, so it is not enough for us to just propose a technique. We must also be able to understand how that technique performs and what are its different properties. And understanding of those properties or the performance of the experiment for a fixed size of the sample, that sometimes becomes difficult to mathematically analyze that. So we generally, or we many a times take resort to what is called asymptotics. Okay. So this is a term that you will keep on hearing, asymptotics. So the point is that suppose we have a statistical procedure, call this P, which is based on our data, x1 is to xn. Okay. This is the x1 is to xn is my data, or you might call it a sample, and I have a procedure P based on x1 is to xn. It could be in any procedure. So many a times the evaluation of performance of P becomes difficult for a finite size of the sample. Okay. That is when n is finite. Okay. So for a particular given value of n, that might be difficult. So we take resort to the hypothetical scenario of letting n to grow to infinity. Okay. So for instance, in mathematics also, you see that sometimes when you're trying to understand a function, it is sometimes often better to understand certain limits of that function. So if you let x to grow to infinity, or if you let t to go to 0, things of this kind. And such limits are quite often easier to calculate and gives us better knowledge of the function, how the function behaves, and so on and so forth. Okay. Also, understanding what happens to P of x1, x2, xn as n goes to infinity is useful to judge whether the procedure is meaningful or not. Why do I write that? Because if you let n to grow to infinity, then obviously the more samples you have, as I said earlier, the more samples you have, or the more data you have from the experiment, will only let you understand the experiment better. So if you know all of the possible, suppose for example, you're doing this coin tossing experiment. So if you know all of the possible outcomes that you can get from the experiment, then it's almost tantamount to saying that I know the experiment in and out. So if that is the case, then this procedure that I have given or proposed, the P of x1 to xn, then that should be able to really capture whatever I want to understand from that system, or for that experiment. But if I see that as n grows to infinity, my P of x1, x2, xn still has something lacking, then obviously that is not a very good procedure, because I have given you all of the information that you could have got, but in spite of having all of the information, you are still not able to give me a good understanding of the system. Hence, your proposed procedure has some flaws. Okay? So this is also another reason why we want to study the asymptotics. Okay? So this procedure, this technique of letting n to grow to infinity is called asymptotics, or sometimes people call it as asymptotic regime, or sometimes people call it limiting behavior. There are several analogous names. Okay. So, is there any questions thus far about whatever I have said?
No, sir.
Okay, fine, good. So, if that is the case, yes. So, if that is the case, then what we would try to now do is to give you some a bit of formalism about what are the things that we do in asymptotic statistics. Okay. So, the first is what we call convergence of random variables. So we deal with convergence of random variables, and there could be several such convergence of random variables. So one is obviously convergence in probability. The other is convergence in distribution. The other is convergence with probability 1. So you all have already done a course on general measures and all. Have you done your analysis 4 course as of yet? Or will you be doing it this semester?
So we have already done a course. We did it last semester.
Have you already done your analysis 4 course? You have already done that.
Yes, sir.
Okay. So you know
Yes,
what
sir, we did it
almost
last.
sure means and so on and so forth. Okay. So this is sometimes called almost sure convergence. And there's a fourth mode of convergence called convergence in LP. You all have seen. This is also called convergence pth moment. So these are several notions of convergence. Some are stronger than the other, some are weaker than the other, some implies the other while not, and so on. Okay. Let's look at each of them carefully. The first is convergence in probability. And so the way I will define all of these things, you might not immediately see how it connects to statistical inference, but believe me, I will give you connections later on. I mean, how these definitions are useful when we actually tackle the problem of statistical inference. But bear with me for some moment to look at these definitions in a very general. Okay. Oh. So what is convergence in probability? So suppose let Xn be a sequence random variables defined on the same probability space. We say that Xn converges in probability to X. That's how we write it. If for any epsilon positive, the probability that mod of Xn minus X bigger than epsilon, this goes to 0 as n goes to infinity. Okay. So essentially, this Xn minus X is becoming more and more concentrated near 0. So the probability outside the epsilon wall around 0 or the epsilon wall around X, that probability is going to 0. Okay. So let's see an example. So suppose I have that x1, x2, dot dot, xn, dot dot dot. All of these things are IID following a uniform distribution in the interval 0 to theta, okay, where theta is positive. And suppose I define my Mn to be the maximum of x1, 2. So that is say, so think of an experiment of this kind where you have observations which are generated from some uniform distribution. So of these and what uniform distribution, that you do not know. So you know that the left endpoint is 0, but you are unsure about the right endpoint. You don't know whether the right endpoint is theta or not. Okay? So this theta is what is unknown. So earlier when I was talking about you are proposing a
So there are
class of
finite
models for a particular statistical experiment or for a particular probabilistic experiment, you can think of this as the first example of that sort. Hello? Yes? Someone was asking a question.
So there are finite points, right? X1, x2 to xn. Like after that, the dots.
You have a question. No, x1, x2, xn are observations that you are getting. So these are say n many observations, and based on the observations you calculate the maximum. Okay. But the unknown parameter here is this theta. Okay. So you have proposed a family of distributions which are uniform distributions in the interval 0 to theta, but which theta is the truth, that you do not know. Okay. So in order to do that, so we will come later to more details. But one good way of trying to understand what the unknown value of theta is to calculate the maximum. Okay. And why this is the case, that we will come later, but at least for the time being, just believe that one good way of trying to understand what the true value of theta is this calculating the maximum. Okay. So now I want to understand. So this is the question that I would ask: does Mn converge in
Sir, is this similar to like the MLE?
And why is this question important? Because look at what would happen if Mn would converge in probability. Yeah, I mean the Mn is the MLE, but let's not go into that part as of now, because the fact that Mn is the MLE really plays no particular role here. But we just want to understand what happens if Mn converges in probability to theta. If I want to show that Mn converges in probability to theta, what will happen? So this is what I have to show, right? I need to show whether this goes to 0 as n goes to infinity. Now, what does it mean to show that probability mod mn minus theta bigger than epsilon goes to 0? What it means is the following. So obviously, you note one thing, that because these are observations from a uniform distribution, the maximum of x1 to xn will always be smaller than theta, because the observations cannot exceed theta. Okay? So this probability is nothing but probability theta minus epsilon, or mn less than theta minus epsilon, because mn cannot be bigger than theta plus epsilon. Okay. So I want to show that this probability goes to 0. What is this showing? If I can show this for every epsilon positive, what it is telling me is that if I keep on increasing the size of my data, that is, if I keep on getting more and more data, then this maximum that I am getting will start becoming arbitrarily close to the true parameter value theta. And this is precisely why the notion of convergence in probability is so useful when dealing with statistical inference. So if I can show that this mn converges in probability to theta, then I'm showing that the probabilities of this kind, they go to 0. That means whatever or howsoever small epsilon you choose, the probability that mn will be epsilon apart, or epsilon, or at a distance of more than epsilon from theta, that probability will go to 0. Okay. Alternatively speaking, the probability that theta minus epsilon less than mn less than theta, this will converge to 1 as n goes to 0. So mn will always, or mn with a very high probability will theta and theta minus epsilon. So what that tells me is that if I now use mn as a proxy for theta, or as an estimator of theta, then I am doing good. Okay? Because this is a good estimator of theta. Okay? So let's now. So is this understandable? Why the notion of convergence in probability is useful? Yes.
So can you repeat this thing again, like this like from the part where you started, where p of mn minus theta greater than epsilon tends to 0?
Okay. So what I'm telling is this, that suppose okay. So the question is, what good thing have I achieved by showing that mn converges in probability to theta? So what I have achieved is that if I can show that mn converges in probability to theta, then these probabilities, the probability that mn is less than theta minus epsilon, these probabilities will go to 0. What does that mean? That means that the probability that my maximum will be at a distance greater than epsilon from theta, that probability is becoming very more samples. Alternatively speaking, the probability that mn lies between theta minus epsilon and theta, that is to say, mn is arbitrarily close to theta, as n grows, that probability is becoming closer and closer to 1. So what it is telling me is that if I use mn as a proxy for theta, I do not know the true value of theta, so I need to have a proxy for it, or an estimator for it. So if I use mn as an estimator for theta, then I am in a good shape, because I know that mn, the probability that mn will be close to theta, epsilon close to theta for any epsilon positive, that probability is becoming higher and higher as my sample size grows. The more samples I have, the better will be my quality of approximation. Is this now clear, Dakshesh? And the quality of approximation obviously will be in probabilistic terms, because we are dealing with random variables here. Is this now clear?
Sir, is this related to like being a consistent estimator? Like as it will increase, it will also the error will also
It is
decrease.
related to being a consistent estimate. I would have just got to that. Yeah, of course. This is obviously related to consistent estimates. I will get to that when we do things of that kind. Okay. So how do we now show that that Mn converges in probability to theta? We need to show that probability Mn less than theta minus epsilon, that goes to 0. So let's calculate what is probability Mn less than theta minus epsilon. So Mn, remember, was the maximum of x1 to xn, that less than theta minus epsilon. So note that saying that the maximum is smaller than theta minus epsilon means that x1 is smaller than theta minus epsilon, x2 is smaller than theta minus epsilon, xn is smaller than theta minus epsilon. So both of these two events are the same. Okay? So now all of these are IID. So what I get is theta minus epsilon by theta whole to the power of n. Okay? And that goes to 0 as n goes to infinity for all epsilon plus. Clear this argument? Have you seen things of this kind with maximums and minimums?
Yes, sir.
All right, so that shows. And okay, so and this is a remark. Ananapam has already said that the fact that this Mn converges in probability to theta is also restated as Mn is consistent for theta, or Mn is a consistent estimator. So both of these statements are the same. But we'll bother about these things a bit later when we actually go into the estimation part and so on. Okay. Okay. So that's nice in a sense. Okay. All right. So that was convergence in probability. The other definition is of convergence in distribution. What does it say? So let xn be a sequence of random variables. We say that xn converges in distribution to x. That's how we write it. If probability xn less than equals to x converges to probability x less than equals to x for all x belonging to continuity points of the CDF of x. Okay. So this is what it is. So what does it say? So it says that if I look at the distribution function of xn evaluated at a point x, then that sequence of distribution functions. So at a point x means these are just numbers, f and x. Okay? Then this sequence of numbers should converge to the value of the distribution function of capital X at the point x. So essentially pointwise convergence of distribution functions. So this is how you can think of it. Pointwise convergence of the sequence of CDFs Fn of xn to the CDF f of x. That's what it is. It's just pointwise convergence. But a little point to note here is that
The presentation stopped, right? Hello? Hello?
are you all able to see my screen?
No, sir.
I guess you are not able to see my screen, right? Okay.
It's not
Okay.
visible.
Let me try. It's a problem that I've been having today since today morning. It's not visible. Okay. Let's see. Still my trouble. There's a bit of a problem. In any case, we're almost done. So see if it works for one last time. Yeah, now it will work. Yeah, good. Okay, so whatever time left, I'll just wrap things up. Okay, so so this was, I was talking about convergence in distribution. So this is pointwise convergence, but we exclude those points which are discontinuity points of the distribution function of x. Okay, so these are the points we just include. So we just check it for the continuity points of the CDF, and the reason for that is that if we need it to be for all points, then that's a somewhat restrictive requirement, and then this would not include more examples of interest. That's why we just require it to hold for only the continuity points of the CDF. Okay. Okay. So what I will do is, so I because we're run out of time. So what I will do is I'll stop here, And I will give you more examples of convergence in distribution from the statistical inference context, and then you will see how all of these definitions kind of connect and what are the different uses of these definitions. Okay? All right, so I will stop here today. So if you have any questions from today's class, or the questions for the course, you're free to ask.
So can you explain why you don't consider all points and only the points of continuity?
Oh, okay. So what happens is that if you include all of the points of or all of the points of the CDF of X, then what happens is that it's a rather restrictive assumption to have, or restrictive requirement to have, because typically at the discontinuity points you might have jumps, okay, and then these convergences need not necessarily happen. I will give you an example in the next class to show that why it is a very restrictive assumption, because if you do that, or if you keep that restriction in your definition, then very intuitive things which you really think should converge in distribution will not hold because of that restrictive assumption. Okay, so I will give you an example in the next class as well.
Okay,
it has more to do
Thank you.
with including more interesting examples than making a definition very restrictive. So that's what it is.
Okay, sir.
Anything else?
Sir, and consistent estimator, that wording, right?
Yes.
Yeah, so that
Yes,
it's like
consistent estimator.
it's like that's the best estimate. Like if we have a finite set of data, we'll take the maximum of that and say that like theta should be somewhere close to that.
No,
This
that
is
is
the
not
thing.
well, this is so consistency is one notion of, as I said, there will be multiple notions of best or good in our course. So this is one desire. I would say it's more of a desirable property. I would not say that this is the only best criteria, but this is obviously a very desirable property to have, consistency. There will be other desirable properties that we will also discuss later on in the course.
Okay.
Sir, like we did a UMVUE, so we will have something like which is the best kind of thing here also. So
Sorry, what?
we did
Can you repeat your question?
like in the stats 1 course we studied about UMVUE, and we got the idea that it is the best, I think. So
Yes.
we will so like there will be something like that also, right, which will be probably the best, or we don't have anything like that. Like, I don't know.
Okay, so no, if when you studied the UMVUE estimator, so that is of course best on base. I mean, that's of course best amongst the class of estimators you are looking for, depending on a particular criteria. So as I said earlier, so in statistics, what is usually the case is that you fix a criteria and you work on that criteria, so that defines your playing field. And once you have a defined playing field, then you can find out a best. Because in general, there is no universal best. That's something that does not work in statistics. There is no universal best. When you define your playing field or you choose your criteria, based on that criteria, there is a best. So UMVUE is best on or is best when you restrict to a particular criteria. When you restrict to another particular criteria, UMVUE need not necessarily be the best. So that is the kind of thing. There is no universal best solution here. And this is true in general in statistics. There is no universal best.
Thank you, sir.
So, but by estimator, we just mean that
Okay. Thank
this,
you all.
like
Then,
the maximum
so
gives
we
an
will-
idea of
Yeah, yeah.
what it.
Maximum gives an estimate. So estimator essentially means a proxy for a particular parameter, or an approximation for a particular parameter based on the sample. That's all that an estimator means. You're trying to estimate something or approximate something.
Right.
And based on the sample, whatever function of the sample that you take, that is estimated.
Thank you, sir.
Okay. All right then. So we will meet. I don't know. When is the next class? Thursday. I think it's Thursday. Okay. So whenever is the next class, we'll meet. All right. Thank you.